So hello everyone, I'm Francesco Tudisco from the GSSI, the Gran Sasso Science Institute in L'Aquila in Italy. And broadly speaking, my research interests are in computational data science. And today I would like to tell you about a problem that arises in this area, which is the problem of link prediction, and how can we actually approach this problem using computational tools. So when you want to work out data sets, you want to do some data analysis from a mathematical point of view, one of the most fundamental tools are graphs. So graphs are mathematical objects, very combinatorial objects, if you want, that are just made out of nodes, so a set of points, set of nodes, and a set of edges or links that connects these nodes. So that describe sort of like relations within these nodes. You see in this figure, for example, we have these dots that are the nodes and links that connect them pairwise in this way. And you can have an undirected graph, which is typically modeling connections that are taking place in both directions. For example, like a friendship relation between two nodes that are, for example, two human beings. Or you can have directed graphs where connections have a direction. Like, for example, in the case where we are modeling, for example, the movement of some good from one region to another region, where these regions are denoted by the nodes in this graph. And in general, graphs or data structure that can actually be described by graphs appear in data science very frequently and in many different ways. So I would just like to give you some examples that you probably have already thought of, and I mentioned some actually just a moment ago already. But just to give you an idea of how broad is this setting. So we can have, for example, social networks, which can model, for example, a group of people, group of students in a class, and these are the nodes, and then we can model with edges exactly friendship relations within these people in this class. So we have or mutual acquaintances or times that these people have been in contact with each other. And this is also, of course, the case of large data sets like Facebook, for example. That's also, if you take the social network itself of Facebook, this is actually indeed a big graph where each page or each account is a node, and friendship relations between users are actually modeled with edges. Then we have, for example, the setting of road networks and the context of graphs. When you want to model a system of roads in a city, for example, you can do this by assigning to each intersection between roads a node, and then modeling through the edges that connect these nodes the road structure of the city. This kind of networks are particularly special because you see here, unlike the previous case, we do have a sort of a geometrical underlying structure, because the nodes, the street, they actually live on the ground, right, on the surface of the earth, and so there is a geometry location that can be added to the network. There are the situation of a citation network or collaboration network in this case, where nodes are authors, for example, and you have edges between them if these two authors have co-authored some paper, they have done some work together. And this is a network of co-authorships among some authors in the network science literature, and the dots are bigger when that author has many collaborators. So these are proportional to the number of collaborators that the authors have here. And we can go on more and more, of course. There are really many examples. I just would like to give you just a few more, maybe two more, where the situation is slightly different. Instead of having a data set that is already itself a graph or a network by sort of definition, if you want. There is the situation where, for example, we can build a graph ourselves from a just given data set. And we do this by looking at sort of similarities or features that data points in our data set have in common. So one typical example is this similarity graph indeed. Here, for example, I'm thinking of a set of images that are actually digits, handwritten digits like this, the number 8, number 1, number 4. And what we do is we embed these digits in a vector, in our n, and then we look at distances between these vectors, and we add an edge between two images that are the nodes of our graph if those two images are close by enough in this space. So you see, this is more or less to say, this drawing here is to say that we sort of draw, like spheres around each image that have the radius as the distance that we are interested to measure, and all those points that fall inside this sphere, we add an edge for those. And so that's something that you get. That's another example. And final example is again related to images. This is called affinity graph, where we have two images and we have two sort of mark points here, like important points that we want to take into account for some reasons. And what we can do is we build graphs where the nodes in the graph are actually these points that are representing the same object in the two images, and we try to match them with affinity properties, and that also gives rise to a graph. So now, this is just to give you an overview of the fact that graphs really appear everywhere. And now I would like to go a little bit more into the details of what link prediction is, what the problem of link prediction is. So, so this is a quite typical problem that arises in the context of data science and in computational data science in particular. And the setting here is that we have a graph that we have modeled from a data set in one of these different ways that I have just discussed, or other ways. And then what we want to do is, okay, we want to predict whether or not certain edges that are not there, there should actually be there. And the situation why we could be interested in doing this is typically because of two reasons. One is that our data set is actually changing in time. And so, for example, we have measured our social relations in Facebook today, and we don't want to do this measurement again tomorrow, but we would just like to say, okay, if this group of people are friends, probably that other person will soon be friend of them as well. So there will be a new edge there. And so we would like to predict that without having to buy again the data set from Facebook. Or another situation is where we are measuring stuff and we're measuring a data set, and we sort of know, we expect that there is some noise in this measurement that we're doing, and this noise can actually lead to some missing edges. So we would like to, fix the measurement that we have done, repair the noise that we have created by adding some missing edges. And we want to do that in a clever way. Now, how can we do this in practice? So one idea could be, okay, let's take all our missing edges in the graph. So we take any 2 points, any 2 nodes, and we consider only those pairs of nodes that don't have an edge. And then we can say, okay, let's assign to this missing edge a score. And this score should be sort of like giving us a probability that that edge that is not there should actually be there. So the larger is the score that we assign, the more likely that edge should be in the graph. And then the point is, okay, how can we compute in a clever way this score, the link prediction score? So one possible idea, which is one of the most naive, one of the first one that came out, is to say, okay, let's compute the distance for a given node, input node 1, for example, or node U. I compute for all the nodes that are not connected to U, I compute the distance, the shortest path distance in the graph between that node 1 and the other nodes. So, for example, in this case, we look at node 1 and we look at node 6, for example, we compute the shortest path distance. So what's the smaller number of edges that I have to cross to go from 1 to 6? In this case, it's 1, 2, and 3, so the distance is 3. And then I do the same thing for all the missing connections between one and the other points. And then what I do, I say, okay, I can imagine that nodes that are closer by, according to this distance, are more likely to be, missing an edge. They're probably somewhat similar, and so probably there should be actually an edge there. So what I can do, I can rank or assign a score to these missing edges by looking at the reciprocal of these distances and rank the missing edges according to this reciprocal. So in this case, you see the distance between 1 and 5 is now 2, and so I assign a score 1/2 to this missing edge here, the edge 1,5, and I assign a score 1/3 to the missing edge 1/6, and so forth. Then I order this scoring, and if I am interested in guessing whether the 3 missing edges, I would take the first 3 entries in this list. Right, so that's one idea. Now let's see a more mathematically robust and meaningful model to measure these scores. So so the idea of this other model is based on this concept of a random walk on the graph. Now, very briefly, what are we going to do? So we're going to sort of model a person that ideally is moving along the graph, following the edge structure of the graph, the one that we actually have, and choosing to move along one of these edges with some probability. So for example, we can say that at the node, if we are at some time at node I, we can move only following the edges that outgo from I, and we choose to go along one of these edges with a probability that is basically 1 over how many edges do we have. So basically we choose at random, we throw a dice with as many faces as the number of outgoing edges that we have, and the number comes out, we say, okay, I go along that edge, right? So if Pij is this probability, so the probability that if I am at node I will go to node j, then this probability can be written like this, right? It's 1 over how many neighbors the node I has. And of course, it's probably 0 if I has no neighbors. So I cannot move from there anymore. So that's the concept of a random walk that we are interested in. And that's in particular the random walk that we are going to consider for this problem. And now what is the idea? How can I connect this with ranking missing edges? Well, what I can do is to say, okay, let's consider now a pair of nodes that are not connected, node U and V, and let's compute what is the expected number of steps that a random walker that is moving in the graph following this random walk would take to move from point U to point V. That is, again, sort of measuring a distance between these 2 points. So how far, in a way, is a U from V? And so we can then measure the similarity or the score of the missing edge UV by looking at the reciprocal of this number. So that's another score, different from the shortest path distance, which is the one that we're going to, that we're interested in. I should say that this score has a little drawback. And the drawback is that, you see, if we are looking at the specter point, number of steps from point U to point V, what happens is that we start, moving randomly in the graph, and then very soon we end up quite far from U, because we start in U, we move, we end up very far from U. And so what happens is that we sort of lose track of what is going on in the neighborhood of U, which is typically where actually we're interested in looking for missing edges, if we're interested to look at missing edges for the point from starting in U. So what people typically do is to modify this random walk slightly by considering this restarted random walk, or also called rooted PageRank random walk, where basically what we do is just say, okay, instead of just deciding to move along my neighbors, what I say is, okay, with probability alpha, for some alpha, I move following these neighbors, as I was doing before. But with probability 1 minus alpha, I restart my random walk. So I jump back at the very beginning, node U, where I started this random moving in the graph. Right, so this is the restarted random walk, or rooted PageRank random walk. And that's what we're going to consider. So overall, how are we going to measure the score of a missing edge, where we look at the potential missing edge between node U and node V, and we compute the expected number of steps that the random walker that moves along the graph with this restarted random walk would take to go from U to V, and then we take 1 over that. Okay, so that's the idea. Now, there is a big question here. Okay, we would like to compute this expected number of steps, but how can we do that? And that's where the computational aspects come into the game. And in particular, you will see that we can compute this expected number of steps by using linear algebra and numerical linear algebra in particular. So we're going to use matrices. But so far, we haven't seen a single matrix. So where do the matrices come into the game here? There is a very fundamental tool for mathematics of data science, which is this object called the adjacency matrix of a graph. So if we have a graph, we can describe it in a unique way by just defining a matrix, which is whose entries are just zeros and ones. And basically, this matrix is made like this. The columns and rows are nodes, so correspond to the nodes, and the entries of the matrix correspond to edges in the graph. So basically, we put a 1 in position, for example, here, 1, 4, if there is an edge that connects nodes 1 and 4. Then we put the 1 in position 2, 3, if there is an edge that connects the nodes 2, 3, and so forth. And you see that because here we have undirected edges, which means that we actually have the edge from 2 to 3, but also the edge from 3 to 2. This matrix is symmetric, and each non-zero entry appears twice in this matrix here. And so the non-zeros, you see, correspond to the edges in the graph. And I actually colored them here, corresponding to well, with the same color of the edge that you see on the left-hand side of this formula. And of course, we can have also directed graphs where the situation is slightly different in the sense that we don't have anymore 2 non-zero entries for each edge, but we only have 1. And you immediately see that these matrices are very sparse, meaning that there are a lot of zeros and just very few non-zeros. And this is a very important property that is the one that allows us to make computations in an efficient way with these matrices, even though we have huge data sets. So how can we use these matrices to compute the rooted PageRank link prediction score? So that's the idea. So I'm sorry if you're not familiar with matrix notation, it's not really important. So but just try to follow me here. This very high level idea. So what we can do is you can think a moment at this probability that we were discussing to go from node I to node J as 1 over the neighbors of the node J, and you can, if you think a moment, you realize that you can actually write down this probability as in terms of this adjacency matrix. And then what you can do is you can write this big matrix here, which is called transition matrix of the restarted random walk process, which takes into account for this restart that we were considering. Now, this is again a matrix which can be written in this way, which is sparse and defined in terms of the adjacency matrix. And then what you can observe is that if you want to compute this PageRank score here, so this expected hitting time, you can do that by solving a system of linear equations that involve this matrix here. And in particular, you can do it by solving this system of equations here, which is also called an eigenvector problem for the matrix PU, where our unknown is the vector X here. And then what we do, basically, we look at the entries of this vector, and those entries are going to give us these numbers that we are interested to compute. And so you see that this is a typical problem that appears in numerical linear algebra, but where we have to exploit the graph structure and the data structure. And that's one of the examples of computational data science. How can we solve this efficiently? And we actually can do that, and we can do that on very large networks. So I would like to conclude with just one example to show you that actually this whole mathematical construction actually helps. So what you see here is the comparison between what happens using the PageRank and what happens using the shortest path distance. So here we are taking two networks. This is, I think, a citation network, and this is a social network. And we computed how many of the edges that we predicted using those models are actually correct edges that should have been there. So basically, we take this network, we remove initially some edges, and then we try to predict them back. And what you see here, this is the ratio between the correctly predicted edges using PageRank and the correctly predicted edges using the shortest path approach. You see that this ratio is very often quite larger than 1, even almost 4 times. So it means that the PageRank is predicting 4 times better than the shortest path approach. Okay, so with this example, I would like to conclude. I hope you found this presentation interesting. And if you are interested in more details, well, you can have a look at my webpage or some of these papers where I've been working on topics related to the link prediction and how to compute these things in a visual way. And this said, I thank you very much for your attention, and